Okay, so that's a lot about the nucleus and a little bit about electrons, but the nuclei are not what is directly involved in chemical reactions. Chemical reactions occur when we make and we break chemical bonds. And these chemical bonds are interactions between electrons. The electrons are the things that are making up these bonds. So let's talk a little more about that. Okay, so as I told you before, electrons orbit around the nucleus like planets around a star. The orbit is called an orbital, the path an electron follows, and atoms are most stable when that valence shell is full. So bonding is all about atoms trying to fill their valence shell with electrons. And there's a couple of different ways that they can do that. So chemical bonds are how we form molecules. We combine elements together to form different compounds. Now, our bodies, as you know, are made up of a number of different types of elements. And those atoms and those elements are rearranged into different types of molecules. So we're going to talk a little about how those are formed. So there are two types of bonds that are intramolecular. So within a molecule, you have atoms that are bonded to each other. The two types there, one that's called covalent and then ionic bonds. But we can also have bonds that are not as strong, that are intermolecular. So one molecule interacting with another molecule. And the one that I want to tell you about, those are called hydrogen bonds. Okay, so a covalent bond occurs when atoms share their outermost electrons, their valence electrons. And when this happens, they are going to share a pair of electrons. So two electrons are going to occupy an orbital, and the electrons are going to orbit both atoms. So here you can see a couple of representations of covalent bonds. So in hydrogen gas, you've got two hydrogen atoms. Now, hydrogen is element number 1. It has 1 proton in the nucleus, which means it has 1 electron in a neutral atom. And in its valence shell, the first valence shell only has 2 electrons. So in order to be most stable, hydrogen needs to have effectively 2 electrons in that valence shell. So if you have 2 hydrogen atoms, they can share a pair of electrons and they can fill that valence shell, and they're very stable. With oxygen gas, O2, that you are breathing right now, which is keeping you alive, their valence shell in O2 has 8 electrons. So in order to fill the valence shell, oxygen is element number 6. No, oxygen is element number 8. Excuse me. Which there's 2 electrons in that first orbital, which means there's 6 in the second orbital. So it needs 2 more to fill that outermost valence shell. So in order to do that, they share not 1 but 2 pairs of electrons. So in oxygen gas, you can see in this what's called a Lewis dot structure here, each of these oxygen atoms is surrounded by 8 electrons. And the way they do that is they have 1, 2, 3, 4, 5, 5, 6, 7, 8. This one has 1, 2, 3, 4, 5, 6, 7, 8. So they're sharing these 2 pairs. So it's like both of them have 8 electrons, even though the way that they're really doing that is by sharing those 2 pairs of electrons. Now, those are both examples of covalent bonds just between one type of atom. When we combine more than one type of atom, 2 different elements, for example, that's when we form a compound. So water is an example of a compound. In the case of water, good old H2O, it's going to have 2 covalent bonds. Again, oxygen wants to share 2 pairs of electrons, form 2 covalent bonds. So it does that with 2 different hydrogen atoms. Remember, hydrogen only wants one electron to complete its valence shell. So it's going to share one of its electrons with an oxygen atom, and another hydrogen atom is going to share one of its electrons with the oxygen atom. And that's how you have H2O. Down here is methane, which is CH4. Methane is a colorless, odorless gas. Yes, I said it's odorless because it is. If you ever thought you smelled methane, you have not. It's if you get methane from commercially, if you actually buy a tank of methane, they odorize it so you know if you have a leak because you don't want methane to accumulate and have a spark ignite it and have an explosion. If somebody has, say, consumed a burrito and released some gaseous product after that, and you feel like you smelled it, what you're smelling is not the methane, what you're smelling is hydrogen sulfide, different molecule. Anyway, methane is CH4, one carbon atom, and 4 hydrogen atoms. So carbon forms 4 different bonds because it has 4 valence electrons. So it wants to fill its valence shell, have 8 total. So in order to do that, it can form 4 of these covalent bonds, share 4 pairs of electrons. Okay? All right, polar covalent bonds. This is like a covalent bond, but it's a little bit different. It is a covalent bond. So the sharing is not always equal. Okay, so not all atoms like to share to the same degree. Some have a higher affinity for a particular electron. Oxygen, which is, again, it's element number 8. Oxygen is very greedy for electrons. Oxygen tends to draw electrons to it. It really likes to pull electrons away from other atoms, other molecules. So even though water has 2 covalent bonds, one between each of the hydrogens attaching to the oxygen, those electrons are going to spend more time spinning around the oxygen atom than they are around the hydrogens. And this creates partial positive and negative charges because they're still sharing the electrons, but it's not even sharing. So imagine that like you and your friend wanted to share a car. You went out on a car together and you drive the car 5 days a week and your friend drives the car 2 days a week. That's kind of like how the electrons are with oxygen. The oxygen atom is driving the electrons 5 days a week most of the time. So it's really more, the car is more yours than your friend's if you're driving it 5 days a week, right? And we express that. You can see there's these little squiggles with, here's a squiggle minus and here's a squiggle plus. Here's a squiggle plus. That's a lowercase letter delta. And that indicates we have a partial negative charge and a partial positive charge, okay? Opposite charges do attract, so that's going to be significant when we talk about water. We're going to spend a lot of time talking about water. Okay. So, we talked about covalent bonds. We talked about polar covalent bonds. Now let's talk about ionic bonds. Ionic bonds occur when with a different type of atom. In some cases, maybe an atom only has 1 valence electron, 1 electron in its outermost shell. Like sodium. Sodium has 1 valence electron. So in order to fill that valence shell, well, the first thing you might think is, well, it needs 7 more to have an octet, to fulfill the octet rule. So that's one thing sodium could do, but sodium doesn't want to do that. picking up 7 more electrons is a lot of work. So what sodium does is like, you know what, I'm going to get rid of this electron. I'm just going to give it to somebody else. And that way, so instead of this orbital being the valence or valence shell, this orbital inside is going to be the valence shell, and it's got 8 electrons, so sodium is stable and happy. And who's it going to give it to? Well, it's going to find another atom that has 7 valence electrons, like chlorine. 1, 2, 3, 4, 5, 6, 7. So chlorine's like, man, I really could just use another electron to fill my valence shell. I'm not going to get rid of all 7 of these, so I really just need that one. So sodium and chlorine arrange that sodium atom is just going to give that electron away to chlorine. Chlorine's going to be like, thank you very much, sodium. And what ends up happening is you've got a sodium ion, because you have 1 fewer electron than you have protons in the nucleus. That's going to form a positively charged ion. Ions are always charged particles. It's positively charged. We call it a cation. Chlorine picks up that electron, and now it's got 1 extra electron than it has protons in the nucleus. So it's going to become a negatively charged ion, or an anion. We put them together and we get sodium chloride, which is table salt. Interesting story. Pure sodium and pure chlorine are nothing like table salt. Pure sodium is a metal. It's a soft metal. You could cut it with a butter knife. But it's very strongly reactive. It's so eager to get rid of those electrons that if you expose it to air, it'll react. If you put it in water, it will explode. Okay, so you've got explosive metal with sodium. Chlorine, as you may know, is the stuff they put in pools to kill germs. Chlorine gas was used as a chemical weapon in World War I. Was banned by the Geneva Convention because if you breathe chlorine gas, you will die. And you will die very unpleasantly. So take this poisonous green gas and this explosive soft metal, and if they don't have their electrons just the way they like them, you're not going to like them either. But if they are stable, if they have the right complement of electrons, they make your food taste better. So those positive and negative charges attract each other so that when they're not in water, sodium ions and chloride ions can stack very neatly in these nice geometric shapes. So here's a salt crystal. Here's some salt with all of the water taken out of it under magnification. If you were to look at it, you see how it's very rectilinear, very boxy. And the reason for that is because at the atomic level, you've got this nice, neat stacking of sodium ions and chloride ions. So an ion is any charged atom or molecule where the number of protons is different from the number of electrons. If it's positively charged, we call it a cation. I imagine like a drawing of a kitty cat with pluses for eyes, and I think, oh yeah, a cation. And then how do I remember anion? Is the negatively charged ion. I just remember it's not the cation. And I do this so much that I just remember that cations are positive and anions are negative. So pretty much to a chemist, any ionic compound is going to be called a salt. Not assault, like it's going to beat you, but salt. So table salt is typically what we mean by sodium chloride. But there are other salts out there. Like you can go to your drugstore, your pharmacy, and get Epsom salt. Epsom salt you don't want to put on your food. Epsom salt you may have used to soak after you've been doing some exercise. If you've got sprains or bruising, an Epsom salt soak is great. If you're having problems with constipation, you can make an Epsom salt drink. It's a saline laxative, so you can drink it and it'll fix that problem for you. But Epsom salt is not sodium chloride, it is magnesium sulfate. So it has a magnesium atom and a sulfate ion. Magnesium has 2 valence electrons it wants to get rid of, and this sulfate ion, which is a sulfur atom and 4 oxygen atoms, has a net charge of -2. So they go very well together. And in this little dry box here, they form these nice crystals that are just like a salt, like table salt. And in that environment, that dry environment, those ionic bonds are strong. What happens when you put them in water? Things change. We'll talk more about that when we talk about water. Okay, so hydrogen bonding is an artifact of polar covalent bonds. Another way of saying that is that hydrogen bonds happen between different molecules because we have polar covalent bonding. So remember, oxygen is greedy for electrons. It sucks the electrons towards that atom. It sucks it away from the hydrogen atoms. So they are a little bit positive, while the nitrogen atoms here in ammonia is a little bit negative, because nitrogen is a little bit greedier for those electrons than the hydrogen atoms in ammonia. So they're attracted to each other. This partial positive and this partial negative charge is an attractive, it attracts these things to each other. And it makes these molecules stick to each other for a little bit, for just a little bit of a second. It's not a permanent bond. It's a transient bond or a temporary bond in most cases. But in great numbers, it adds up. So hydrogen bonds are between different molecules, not within a molecule. They are kind of sticky interactions. And in great number, they can do a lot, but even water, as we're going to find out in the next lecture, is a strange substance, which is a weird thing to hear the first time you hear it, but I'll explain when we get to the next lecture. Why is water such weird stuff? So finally, I just want to tell you, chemical reactions are what happen when we make and break chemical bonds. So if you've ever heard of a chemical reaction, which you probably have, what's really happening at the atomic level, the molecular level, is that bonds are being broken, bonds are being made. So we can take, for example, 2 molecules of hydrogen gas, combine that with a molecule of oxygen gas, and end up with 2 molecules of water. And in order to do that, we have to break those 2 bonds there, break this bond here, break this bond here, make new bonds, form new bonds that are in our products, which are water. So that's what a chemical reaction is. It's a breaking and making of chemical bonds, which, remember, that's interactions between electrons. Okay, so let's review those 7 learning objectives. I'm not going to read them out for you. I'm going to let you stop and take stock. And then the next video, we'll move on to the next part, which is all about water.